This is the last lecture in chapter 16 about acids and bases, and this is a summary of Lewis acid and bases. We've talked about 3 different theories or definitions of acid and bases. The original one was the Arrhenius theory, which is the most limiting. That's why it's shown as like a small circle. And then probably the most common one and more current is Brønsted-Lowry theory. So Arrhenius was something would have to produce hydronium ion in water or hydroxide in water. So to be an acid or base, it had to be in water. Then the more recent, more inclusive theory is Brønsted-Lowry theory, which said that an acid was a proton donor and a base, excuse me, is a proton acceptor. And now the most inclusive definition of all, Lewis acids and bases. And if you're going on to take organic, that would be a real important concept, is the most inclusive of them. And as you will see, we'll go more into it in the PowerPoint, but a Lewis acid is an electron pair acceptor. So rather than talking about hydrogen ions, doesn't even have to have a hydrogen ion. And a base is an electron pair donor. So in table form, here's what I just kind of went over, the 3 different definitions. So you should definitely be familiar with all of these definitions for hopefully an easy multiple choice question about them. So let's go over exactly what the definition of a Lewis acid and base mean. What are they talking about? So a Lewis acid is a substance that accepts a pair of electrons. Okay, so you can kind of visualize it down here. And those pair of electrons will be used to make a covalent bond between 2 substances. So clearly, if a Lewis acid accepts an electron pair, it must be electron deficient. It must be able to accommodate those 2 extra electrons. So a Brønsted-Lowry acid is also typically a Lewis acid if it has a acidic hydrogen ion, right? Because an acidic hydrogen ion is deficient, right? It's H+. And so in a Brønsted-Lowry acid-base reaction, we can also think of the hydrogen ion that is accepting the electrons or that is moving over to a base, bonding with a base, as a Lewis acid also. Other things that you'll commonly see as Lewis acids, but that are not Brønsted-Lowry acids, would be, for example, BF3. BF3 is electron deficient. We know boron's a moron, right? Boron is stable with 6 valence electrons instead of 8, but because of that, boron has an empty orbital that can accommodate an extra pair of electrons and form an extra bond. So it's a really good and very common Lewis acid. Now, a Lewis base is a substance that has a lone pair of electrons that it can donate to an electron deficient species to make a covalent bond. So the primary requirement to be a Lewis base is it has to be an atom with a lone pair of electrons. So we see that very commonly on neutral nitrogen containing substances, right? There seems to always be one lone pair. We see it on oxygen containing substances. So any substance with at least one lone pair of electrons can serve as a Lewis base. Commonly, Lewis bases will have negative charges too. Anything with a negative charge is going to have at least one lone pair of electrons. So a few more examples and a little bit more detail of Lewis acids. Here's kind of a model, a boron containing compound. And again, because it's stable with only 6 electrons, boron-based molecules have an empty orbital, and that is necessary in order to accommodate the lone pair of electrons that's being donated by the Lewis base. So there are 2 types of Lewis acid-base reactions that you will commonly see. One is that this is called an adduct, where the 2 electrons donated by the Lewis base make a new covalent bond between the 2 substances, and nothing else changes, just a new bond. No bonds are broken, just a new bond is made, and that's an adduct. You just kind of stick the 2 together. Now, there are going to be charges involved. The nitrogen now has a formal charge of +1, and boron is going to have a formal charge of -1. And common Lewis bases, again, they have to have a lone pair of electrons. So, as I said before, you'll see nitrogen, oxygen, phosphorus, sulfur species all participating in Lewis acid-base reactions. So here's a typical Brønsted-Lowry acid-base reaction, right? If you glanced at it, you would say, yeah, okay, here's the acid, because I know hydrochloric acid for one thing, but also it starts with a hydrogen. Hopefully you've remembered my zillion statements that tell you neutral nitrogen-containing compounds are weak bases. And say, okay, yeah, that's a Brønsted-Lowry acid-base reaction, which is true. It is. The hydrogen on the acid is transferring to the base, and the chloride anion is left over. But it turns out that this can also be classified as a Lewis acid-base reaction. So let's make sure we understand how that's done. In this case, the Lewis base is the nitrogen. Remember, a Lewis base has to have at least 1 lone pair of electrons that is being used to make a new bond. And the Lewis acid or electron acceptor really is the H plus on the HCl. And while some Brønsted acids are also Lewis acids, not all Lewis acids are Brønsted acids, all right? So let me say that again. Not all Lewis acids are Brønsted acids. And that's why if you remember the cover page where I showed that Lewis acids is the most inclusive definition of acid bases. It has the most substances. So not everything that's a Lewis acid is a Brønsted-Lowry acid. And a good example is boron-containing components, right? You could not describe this reaction as a Brønsted-Lowry acid base. You couldn't do that because there's no acidic hydrogen involved. All right, so that can only be described as a Lewis acid-base reaction. Some common Lewis bases and acids, just to because it can feel kind of foreign in the beginning, so just to kind of have on hand to get used to how to identify them. So the most important skill you're going to need to be able to do at this point is identify a Lewis acid-base reaction, identify the Lewis acid, identify the Lewis base, and you will probably be expected to predict products if I were to give you a Lewis acid and base and ask you what the product is. For example, the one I've been showing you a lot of now. You should be able to write the products of that. So, as I mentioned a couple slides ago, the most common type of Lewis acid-base reactions will be one of 2 types. The one we've talked about most is formation of an adduct, and that's when you make a new bond between the 2 substances reacting and no bonds are broken. You simply join the 2 substances together in an adduct. Now, there's another common type of Lewis acid-base reaction where you make a new bond, but you also break an old bond. And so, for example, if NH3 were reacting with water, the lone pair on the nitrogen in NH3 would be used to make a new covalent bond with one of the hydrogens in water. But in turn, because this hydrogen we know cannot handle two bonds, right? So the things that make adducts, the substance that's being made a new bond with, can handle the extra electrons. It has an empty orbital. In this case, hydrogen can't handle two bonds, so a bond breaks. Okay, one of the old bonds breaks. And so you end up with two new products. Now, this would be more commonly described, right, as a Brønsted-Lowry acid-base reaction. So the displacement mode of Lewis acid-base are often Brønsted-Lowry type reactions, okay, where an acidic hydrogen is transferred to the base. And then, of course, we have the conjugate acid and conjugate base form, two products formed. So, as I said a couple slides ago, you need to be able, if I show you a reaction, you need to be able to identify what is the Lewis acid, what is the Lewis base, as well as predict products. So, again, you've seen this a number of times already in this PowerPoint. But you would have to be able to say, okay, that is the Lewis base, this is the Lewis acid, and that is an adduct from a Lewis acid base reaction. And that is it for Lewis acid base. So make sure you go through the practice problems on the worksheet uploaded in D2L so that hopefully this will be an easy section of the next unit test for you.